I'm so glad you found your way here. Right now, a visitor from another star system is passing through our cosmic neighborhood, carrying secrets from a world that formed billions of years before Earth existed. Tonight, you'll discover how 3I Atlas reveals the hidden connections between stars, and by the end, you'll understand why we've never truly been alone in this galaxy. Welcome to Get Sleepy Science. Wherever you are right now, perhaps looking up at the darkness between stars, or simply feeling the quiet weight of night settling around you, allow yourself to rest in this moment of cosmic stillness. We'll drift through 100 space facts about the universe's hidden pathways. From cold emptiness where ancient travelers journey for billions of years, to the moment a telescope caught light from another world, to the realization that space is far more connected than we ever imagined. These quiet journeys through space create a cosmic community of peaceful minds. A gentle like and subscribe helps other sleepless souls discover this sanctuary too, one sleepy soul at a time. Your presence here, listening to stories written in starlight, means the universe to us. Settle deeper into your pillows now. Let your shoulders drop, your breathing slow and steady. You don't need to hold on to any of this cosmic knowledge. Just feel that peaceful heaviness spreading through you, like you're floating weightless in the vast, silent darkness between stars, drifting gently towards sleep. Close your eyes and breathe deeply. You're floating where starlight paints pathways through infinite space. Let your mind drift with cosmic silence. And now, we begin. On July 1st, 2025, a telescope in Chile spotted something extraordinary. Scientists using the Atlas telescope system noticed a faint smudge of light moving through the constellation Sagittarius. At first, it looked like just another comet, but as astronomers around the world turned their instruments toward this mysterious visitor, they realized something remarkable. This object wasn't born in our solar system at all. Its speed and trajectory told an unmistakable story. It came from the space between stars, from a planetary system orbiting a sun we'll never see, traveling for perhaps billions of years through the dark before finally arriving here. They named it 3I Atlas, the third known interstellar object ever discovered passing through our cosmic neighborhood. For only the third time in human history, we were witnessing a messenger from another star system, carrying secrets from a world beyond our reach. The discovery of 3I Atlas happened almost by accident, the way so many profound moments in astronomy do. The Atlas telescope system wasn't even looking for interstellar visitors. Its purpose is planetary defense, watching for asteroids that might someday threaten Earth. But on that summer morning, its automated detection system flagged an object moving strangely through the sky. Within hours, astronomers began gathering older images from telescope archives, searching backward through time. They found pre-discovery observations dating back to June 14, 2025. The comet had been visible in photographs for weeks, just waiting to be noticed. These archival images helped scientists calculate its path with incredible precision, confirming what the initial observations suggested. This visitor entered our solar system from the depths of interstellar space, bringing with it the first tangible evidence that the galaxy beyond our sun might be far more active, far more connected than we once believed. Before 3I Atlas arrived, our understanding of interstellar space was shaped by absence. When you look up at the night sky and see the darkness between stars, it seems empty, almost completely void. Astronomers once thought that the vast distances separating star systems were crossed only by light and perhaps the occasional rogue planet ejected from its home world and wandering alone forever. The space between stars appeared to be exactly what it looked like: nothing. cold, dark, silent, and utterly isolated. Each star system seemed like an island, separated from its neighbors by distances so enormous that nothing material could bridge them within any meaningful time frame. Our solar system, in this old view, was effectively alone. The planets, asteroids, and comets that orbit our sun were understood to be our exclusive family, formed together 4.5 billion years ago from the same cloud of gas and dust, with no connection to any other stellar system. This view of cosmic isolation made intuitive sense for a long time. After all, the distances between stars are almost incomprehensible. Our nearest stellar neighbor, Proxima Centauri, sits about 25 trillion miles away. That's roughly 4.25 light years, which means light itself, traveling at 670 million miles per hour, takes over 4 years to cross that gap. For something material, something solid like a comet or asteroid, making that journey would require countless millennia. Scientists calculated that objects ejected from planetary systems would drift through the interstellar void for millions of years, perhaps billions, before encountering another star. The galaxy seemed too vast, the spaces between its lights too empty, for any real exchange of material between stellar systems. Each sun and its family of worlds appeared fundamentally separate, sharing only the gravity that binds the galaxy together, but never truly touching. When astronomers discovered the first interstellar object in 2017, it shattered this comfortable isolation. That object, named Oumuamua, which means scout or messenger in Hawaiian, tumbled through our inner solar system at tremendous speed. Its discovery shocked the scientific community. Here was proof that the space between stars wasn't truly empty after all. Material could cross those vast distances. Other planetary systems could reach out and touch ours, at least in this limited way. But Oumuamua was puzzling and strange. It showed no cometary activity, no tail or coma of gas and dust. Its shape appeared elongated, perhaps 10 times longer than it was wide. It accelerated in ways that couldn't be explained by gravity alone. Some scientists even speculated it might be artificial, though most disagreed. The mystery of Oumuamua left more questions than answers. 2 years later, in 2019, a second interstellar visitor arrived. Amateur astronomer Gennady Borisov spotted it, using his custom-built telescope from Crimea. This object, designated 2I Borisov, behaved more like astronomers expected a comet should. It had a bright coma of gas and dust, a beautiful tail streaming behind it, and it followed predictable physics. Scientists could study 2I Borisov in detail, analyzing the light from its coma to determine what molecules were boiling off its icy nucleus. They found water vapor, carbon monoxide, and other familiar compounds, though in different ratios than comets from our own solar system. 2I Borisov suggested that comets from other star systems might not be so different from our own. It was reassuring in its familiarity, even as it remained fundamentally foreign, a visitor from another Sunday. After 2I Borisov departed, slipping back into the darkness from which it came, astronomers wondered when the next interstellar visitor would arrive. Based on statistics from just 2 objects, scientists estimated that perhaps 1 or 2 interstellar objects, larger than a few hundred feet, might pass through the inner solar system each year. Most would go undetected, too faint or too fast to spot before they vanished again into deep space. Advanced survey telescopes like ATLAS and the upcoming Vera-C Rubin Observatory would increase detection rates, but finding these rare travelers still required remarkable timing. The galaxy might be full of wandering objects, ejected from distant planetary systems, but the solar system's inner regions, where Earth orbits, represent just a tiny target. For an interstellar object to pass close enough for detailed study required extraordinary cosmic coincidence. 3. I-Atlas changed these calculations in a profound way. Its discovery came just 6 years after Oumuamua and 6 years after 2 I-Borisov. 3 confirmed interstellar objects in 8 years suggested these visitors arrive more frequently than early estimates predicted. Either the galaxy contains far more wandering comets and asteroids than scientists thought, or our detection methods were finally becoming good enough to spot them consistently. The Atlas survey system, spread across multiple sites, including Chile, Hawaii, and South Africa, watches the entire accessible sky every night, automatically flagging anything that moves. As this global network expands and improves, the detection rate should increase dramatically. We may be entering an era where interstellar visitors become almost routine, where astronomy can study these cosmic messengers not as rare anomalies, but as regular arrivals, each one teaching us something new. What makes 3I Atlas particularly special, beyond simply being the third interstellar object discovered, is that it arrived at a time when our observational capabilities had dramatically improved. When Oumuamua passed through in 2017, it was already leaving the solar system by the time astronomers realized what it was. Most observations came after the object had already made its closest approach to the Sun and was heading back out into deep space. By the time scientists recognized 2I Borisov as interstellar, they had more warning, but still limited time. With 3I Atlas, discovered in early July 2025, while still relatively far from the Sun, astronomers had months to prepare. They could schedule observations with the world's most powerful telescopes, plan detailed studies, and coordinate research across multiple observatories. This advance notice transformed 3I Atlas into the most thoroughly studied interstellar object in history. So yes, 3I Atlas is already beginning to change our understanding by showing us that the space between stars might be far busier than we imagined. For centuries, humans looked at the darkness between stellar lights and saw emptiness. We assumed that the fundamental unit of the cosmos was the star system, that each sun and its family of worlds existed in essential isolation, separated by unbridgeable gulfs of space. But 3 visitors in 8 years tells a different story. The galaxy appears to be filled with wandering objects, debris from planetary formation, material ejected by gravitational encounters, ancient comets that have drifted for billions of years. These travelers connect star systems in ways we're only beginning to understand. The darkness between stars, we're learning, might actually be a highway, carrying an endless traffic of cosmic wanderers. The speed of 3I Atlas tells us something profound about its journey. When astronomers measured the comet's velocity relative to our Sun, they found it traveling at approximately 58 kilometers per second. That's about 130,000 miles per hour, roughly 2,000 times faster than a commercial airliner. That might not sound particularly fast compared to spacecraft speeds, but in astronomical terms, it represents what scientists call hyperbolic excess velocity. This means 3I Atlas is moving fast enough to completely escape the Sun's gravitational pull. It's not in orbit. It won't return. After passing through our solar system once, it will continue outward, gradually slowing as the Sun's gravity tugs backward, but never slowing enough to be captured. Eventually, it will exit our solar system at the same speed it entered, continuing its journey through the galaxy. This velocity reveals something else remarkable. 3I Atlas is moving faster than both previous interstellar objects. Oumuamua entered at 26 kilometers per second relative to the Sunday 2I Borisov, came in at 32 kilometers per second. But 3I Atlas, at 58 kilometers per second, is nearly twice as fast as its predecessors. This higher speed suggests a different origin story. The faster an object moves through interstellar space, the more energetic the event that ejected it from its home system must have been. Perhaps 3I Atlas was flung away by a close encounter with a massive planet, or maybe it originated in a more dynamically active stellar system. Its speed carries information about events that happened billions of years ago, countless light years away, in circumstances we can only imagine. The trajectory of 3I Atlas is equally revealing. Imagine drawing orbits around the Sunday. Some are nearly perfect circles, like Earth's gentle path. Others stretch into long ellipses, like the comets born in our solar system's distant reaches. But 3I Atlas follows something stranger, a path so open it barely curves at all. Astronomers measure this using a value called orbital eccentricity. Anything above 1 means the object will escape forever. 3I Atlas has an eccentricity of 6.139, the highest ever measured for any natural object in our solar system. This extreme value means its path is almost a straight line. It passes through our solar system, barely deflected by the sun's gravity, following a trajectory so open that it's almost a pure transit, like an arrow flying through space that simply happens to pass near our Sunday. When scientists traced this trajectory backward, projecting where 3I Atlas came from, they found it arrived from the direction of the constellation Sagittarius. That direction is significant. Sagittarius lies along the plane of our galaxy, toward the Milky Way's center. The comet approached from the galactic disk, the flattened region where most stars reside, rather than from above or below the galactic plane. When scientists trace its trajectory backward through time, some researchers suggest this comet might have been wandering for billions of years, perhaps even predating our solar system itself. This remains speculation, pieced together from mathematical models of galactic motion. But if true, it would make 3I Atlas a fossil from the galaxy's earlier days, carrying within its ice a record of ancient chemistry from when the Milky Way was younger. As 3I Atlas approached the Sun, something beautiful happened. The comet began to wake up. Comets are sometimes called dirty snowballs, mixtures of ice and rock. And when they approach a star's warmth, the ice begins to sublimate, turning directly from solid to gas, without passing through a liquid phase. This outgassing creates the characteristic coma, a bright cloud of gas and dust that surrounds the comet's solid nucleus. It also creates the tail, the streaming banner of material pushed away by solar wind and radiation pressure. 3I Atlas showed its first signs of activity around May 2025, when it was still about 6 astronomical units from the Sun, farther than Jupiter. This early awakening suggested the comet's ice is extremely volatile, perhaps because eons of cosmic radiation exposure had altered its surface chemistry, making it more sensitive to even distant solar warmth. The Hubble Space Telescope captured stunning images of 3I Atlas in late July 2025, when the comet was about 277 million miles from Earth. These observations revealed a teardrop-shaped cocoon of dust trailing behind the nucleus. The images showed the comet as a fuzzy, greenish-blue object, the color coming from molecules of diatomic carbon glowing in sunlight. Because Hubble was tracking the moving comet, background stars appeared as streaks in the long-exposure photographs, creating a sense of motion, as though the comet were flying past fixed lights. These images weren't just beautiful, they were scientifically valuable. By measuring the brightness and extent of the coma over multiple observations, astronomers could estimate how much material was streaming off the nucleus. The dust production rate increased steadily as 3I Atlas approached the Sun, from about 11 pounds per second in early May to nearly 70 pounds per second by mid-July. Size matters when studying comets, and determining the actual size of 3I Atlas proved challenging. The bright coma surrounding the nucleus makes it difficult to see the solid body underneath. It's like trying to measure a light bulb by looking at its glow. Based on Hubble observations from August 2025, scientists established upper and lower bounds. The nucleus is no smaller than about 1,400 feet across, and no larger than 3.5 miles in diameter. That's a considerable range of uncertainty. If it's at the smaller end, 3I Atlas would be roughly the size of the Empire State Building. If it's at the larger estimate, it would be larger than some small moons. Either way, it's substantial enough to have survived billions of years wandering through interstellar space, enduring cosmic ray bombardment and countless tiny impacts from interstellar dust. The cloud of gas and dust surrounding the nucleus, what astronomers called a coma, grew enormous as the comet neared the Sun, with estimates suggesting it expanded to roughly 16,000 miles across at its most active, dwarfing even Earth itself. This vast cocoon wasn't solid, of course, but a diffuse fog so thin that stars could shine through it. Observations from ground-based telescopes and the Hubble Space Telescope measured these changing dimensions as the comet became increasingly active. Jets of gas were erupting from multiple points on the nucleus, carrying dust particles along with them. These jets probably originated from specific areas where ice lay close to or at the surface. As sunlight warmed different parts of the rotating nucleus, new jets would activate while others diminished, creating a constantly changing pattern of outgassing. Color is information in astronomy. When scientists analyzed the spectrum of light coming from 3I Atlas, they found something particularly interesting. The coma appeared reddish, similar to the dust seen around 2I Borisov, but distinct from typical comets born in our solar system. This reddish color comes from organic compounds, complex carbon-based molecules that absorb blue light and reflect red. The color deepened throughout July 2025 as the comet became more active, suggesting that either the surface composition was changing as outer layers sublimated away, or that deeper material with a different composition was being exposed. Some astronomers noted that the reddish hue resembled the color of objects in the Kuiper belt, the region beyond Neptune where many comets originate. This similarity hints that comets across the galaxy might share common formation processes, despite forming around different stars. In early August, the James Webb Space Telescope quietly observed 3I Atlas through its infrared vision, revealing molecules invisible to human eyes. Webb's near-infrared spectrograph could detect compounds hidden from optical telescopes. The data showed strong signatures of carbon dioxide, one of the most volatile ices found in comets. This explained why 3I Atlas became active so far from the Sunday. Carbon dioxide ice sublimates at lower temperatures than water ice, starting to outgas when a comet is still beyond Jupiter's orbit. Ground-based spectroscopy revealed something unexpected: traces of nickel vapor in the coma, an unusual signature not commonly seen in solar system comets. Webb's infrared observations complemented this discovery by detecting complex organic molecules, painting a detailed portrait of this visitor's chemical makeup. Together, these observations from space and Earth created the most complete chemical profile ever assembled for an interstellar traveler. The detection of nickel vapor in 3I Atlas opened an unexpected window into the comet's ancient origins. Nickel doesn't sublimate until temperatures reach extremely high values, over 2,700 degrees Fahrenheit. For nickel vapor to appear in the coma, tiny grains of metallic nickel must be heating up in direct sunlight after being released from the sublimating ice. The presence of nickel tells us something about where this comet formed. The ratio of nickel to other elements, compared with similar measurements from solar system comets, suggests 3I Atlas formed in a protoplanetary disk that had a slightly different chemical composition than the disk that birthed our solar system. This makes sense. Different regions of the galaxy have different metallicities, different abundances of elements heavier than hydrogen and helium. 3I Atlas carries in its chemistry the signature of its birthplace, a stellar system with a subtly different elemental recipe. Organic molecules also appeared in the spectral data from 3I Atlas. These carbon-based compounds form in the cold outer regions of protoplanetary disks, where simple molecules like water, methane, and ammonia freeze onto dust grains and are processed by ultraviolet radiation and cosmic rays. Over millions of years, this processing creates increasingly complex organic compounds. Scientists detected signatures consistent with formaldehyde, hydrogen cyanide, and other simple organics in the coma of 3I Atlas. These molecules are fundamental building blocks for more complex chemistry. Their presence reinforces the idea that the basic chemistry of planet and comet formation might be similar throughout the galaxy. The same physical processes, the same chemical reactions, seem to occur wherever stars form planetary systems, creating comets that, despite being born around different suns, share remarkable similarities. As October approached, 3I Atlas raced toward its closest approach to the Sun, called Perihelion. This would occur on October 29, 2025, at 11:36 Universal Time. At Perihelion, the comet would be 1.36 astronomical units from the Sun, about 126 million miles, placing it just inside the orbit of Mars. This was close enough for intense solar heating, but not dangerously close. The comet would survive its perihelion passage intact. Some comets approach so near the Sun that they disintegrate, torn apart by tidal forces or simply evaporating away, but 3I Atlas would remain at a safe distance. Scientists anticipated that the comet would reach peak brightness and activity around perihelion, offering the best opportunity for detailed observations before it began its journey outward. Ground-based telescopes around the world tracked 3I Atlas throughout its approach. Amateur astronomers with backyard telescopes could spot it as a faint, fuzzy patch in the pre-dawn sky. Professional observatories scheduled time on larger instruments to capture high-resolution images and spectra. The Virtual Telescope project in Italy live-streamed observations, allowing people worldwide to watch this cosmic visitor in real time. There was something profound about this coordinated global effort. Humans on Earth, members of one species on one small planet, working together to understand a visitor from the depths of space. Different nations, different cultures, different languages, all united by curiosity about something that came from beyond our Sunday. The study of 3I Atlas became, in a small way, a project for all humanity, a shared exploration of our connection to the wider galaxy. These early observations of 3I Atlas revealed something crucial. Interstellar objects are not uniform. Oumuamua showed no cometary activity and accelerated mysteriously. 2I Borisov behaved like a typical comet. 3I Atlas falls somewhere between, showing strong cometary activity but with unusual chemical signatures and a trajectory suggesting extreme age. Each interstellar visitor is unique, carrying its own story. This diversity matters profoundly. It suggests that planetary systems across the galaxy form and evolve in varied ways, under different conditions, creating different populations of comets and asteroids. By studying these rare visitors, we're conducting a survey of galactic planetary systems without ever leaving home. Each object is a sample returned from another star system, delivered to our doorstep by the galaxy's own gravity. Pattern is emerging. Space is not empty. Connection exists. Take a deep breath and feel this. Every atom in your body, the carbon, the nitrogen, the oxygen, the iron, was created in the core of a dying star. The telescopes we build, the instruments we point toward the sky, all made from the material of the universe, reaching back toward the universe. Feel yourself carrying the trace of ancient stars. Every breath you take, you're breathing the same atoms that once drifted between suns, traveling through the darkness that 3I Atlas has crossed. We are all made from cosmic dust, connected by the same elements that fill this wandering comet. Now, we continue. As Perihelion approached in late October 2025, 3I Atlas passed behind the Sun from Earth's perspective, becoming temporarily unobservable from our planet. But spacecraft positioned elsewhere in the solar system had different viewpoints. Spacecraft orbiting Mars, including ESA's ExoMars Trace Gas Orbiter and Mars Express, observed the comet from about 18 million miles away during early October as 3I Atlas passed relatively close to the red planet. From Mars, 3I Atlas appeared as a small fuzzy dot against the background stars, its tail just barely visible. These Mars-based observations provided a different viewing angle than Earth-based telescopes could offer, helping astronomers understand the comet's three-dimensional structure and refine calculations of its path through space. The advantage of observing from Mars was more than just a better view. When astronomers observe an object from two different locations, they can use a technique called triangulation to determine distance and position with greater accuracy. Earth-based telescopes and Mars orbiters, separated by tens of millions of miles, provided two distinct perspectives on 3I Atlas's location. By comparing observations from both locations, ESA scientists improved the predicted trajectory of the comet by a factor of 10. This might sound technical, but it matters. Knowing exactly where 3I Atlas is and where it's going allows astronomers to point their telescopes more precisely, capture better data, and understand the comet's path through space with much greater confidence. The improvement came from being in two places at once, using the solar system itself as a giant instrument. ESA's JUICE spacecraft, the Jupiter Icy Moons Explorer, though much farther away than the Mars orbiters, also attempted observations of 3I Atlas in November 2025. JUICE was on the far side of the Sun from Earth, making data transmissions slower, but it had a view of the comet in a very active state, shortly after perihelion, when outgassing would be at maximum. These observations wouldn't be received until February 2026, due to JUICE's position and its limited communication bandwidth. Still, the fact that multiple spacecraft across the solar system could coordinate to study one object demonstrates how far space exploration has advanced. What once would have required a dedicated mission can now be accomplished opportunistically, using instruments already in space for other purposes. After perihelion, 3I Atlas emerged in Earth's pre-dawn sky in early November, visible again to ground-based observers. Amateur astronomers reported seeing it with modest telescopes, 8-inch apertures or larger, as a small fuzzy patch in the constellation Virgo. The comet had developed a complex tail structure, with multiple jets and streamers visible in photographs. These structures revealed that the nucleus was not uniformly active. Instead, certain regions were producing more gas and dust than others, creating the intricate patterns observers could see. The comet was now moving away from the Sun, gradually dimming as it receded. but it remained bright enough for study. Observers around the world shared their images online, creating a collective portrait of this visitor from another star. The brightening behavior of 3I Atlas told scientists something important about its nature. As 3I Atlas approached the Sun, its dust production increased rapidly, following a steep pattern that reminded scientists of dynamically old comets, objects that have evolved over many orbits. But this was 3I Atlas's first approach to our Sun, suggesting instead that the comet itself might be ancient, weathered by eons in interstellar space rather than by repeated solar encounters. This steep activity curve resembles the behavior of comets that have developed thick, processed surface crusts over time. For 3I Atlas, the weathering came not from multiple trips around our Sun, but from billions of years drifting through the galaxy, exposed to cosmic radiation and the harsh conditions of interstellar space. This evidence of age carries profound implications. If this comet is indeed as ancient as its high velocity suggests, perhaps several billion years old, it could carry within its ice a record from when the galaxy was younger, when star formation raged more intensely, when the chemistry of space itself was subtly different. These are tentative estimates, but they paint 3I Atlas as a possible time capsule from cosmic dawn. Such an ancient object could tell us about conditions in the early galaxy, long before Earth existed. The molecules frozen in its ice, the dust grains trapped in its structure, all would be samples from primordial environments. In studying 3I Atlas, we're not just learning about one comet or one distant planetary system. We're glimpsing the galaxy's past. The increased detection rate of interstellar objects forces us to reconsider how planetary systems interact with each other. Planet formation is not a perfectly efficient process. When planets grow in protoplanetary disks, their gravity stirs up the remaining planetesimals, the building blocks that didn't get incorporated into planets. Many of these planetesimals are rejected, flung out of the system by gravitational encounters with giant planets. Our own solar system has done this. The Oort cloud, that vast spherical shell of comets surrounding our Sun, contains millions of icy bodies, but countless others were ejected entirely, sent wandering into interstellar space. Every planetary system probably does this. Every star with planets likely ejects a substantial fraction of its small bodies. The galaxy, we're realizing, might be filled with this cast-off material. Computer simulations of planetary system formation support this idea. When astronomers model the chaotic early years of a star system, they find that for every comet or asteroid that ends up in a stable orbit, 10 or more might be ejected entirely. If this ratio applies generally across the galaxy, then the number of interstellar objects drifting between stars could vastly exceed the number of objects still bound to stars. Some estimates suggest there might be trillions of interstellar comets and asteroids wandering through the Milky Way at any given time. Most are small, dark, and essentially undetectable, unless they pass very close to Earth. But they're out there, filling the space between stars with silent travelers, each carrying the chemical signature of its birthplace, each a messenger from some distant sunday. This population of interstellar wanderers means something important. The galaxy is more connected than it appears. We think of star systems as separate, isolated units, but they're constantly exchanging material, albeit slowly and randomly. An object ejected from a planetary system near one star might, millions or billions of years later, pass through a planetary system near another star. It might even be captured if the encounter geometry is just right. Some scientists speculate that planetary systems might occasionally capture interstellar objects into stable orbits, adopting visitors from elsewhere. Our own Oort cloud might contain some captured interstellar comets, indistinguishable from native-born objects, silent immigrants that arrived from beyond and decided to stay. We might share our solar neighborhood with visitors who never left. The chemistry of 3I Atlas offers clues about its home system. The relative abundances of elements and molecules detected in its coma don't exactly match solar system comets. The carbon dioxide is more abundant, the nickel signature is unusual, and the organic molecules show subtle differences. These variations suggest the protoplanetary disk, where 3I Atlas formed, had a slightly different chemical composition than the disk that birthed our planets. This makes sense given the galaxy's chemical evolution. Stars that formed earlier in galactic history had less heavy elements than younger stars. Stars that formed in different regions of the galaxy inherited different elemental abundances from their parent molecular clouds. 3I Atlas carries this chemical fingerprint, a signature of its stellar neighborhood written in molecules. The idea that each star system has a unique chemical signature is both beautiful and scientifically valuable. It means that by studying interstellar objects, we're effectively conducting a survey of chemical conditions across the galaxy. Each visitor is a sample returned from a different location and potentially a different era in galactic history. As we detect more interstellar objects and analyze their compositions, we'll begin to see patterns. We'll learn which elements and molecules are common across all star systems and which vary. We'll understand how the chemistry of planet formation depends on a star's mass, age, and location in the galaxy. We're mapping galactic chemistry, one comet at a time, using visitors that come to us, rather than requiring us to travel impossible distances to reach them. Water signatures in the spectrum of 3I Atlas appear similar to water in solar system comets, but not identical. The ratio of deuterium to hydrogen, a key diagnostic of water's origin, seems slightly elevated compared to Earth's oceans, but lower than some Kuiper belt objects. Deuterium is heavy hydrogen, with an extra neutron in its nucleus, and the ratio of deuterium to regular hydrogen depends on where and how water ice formed. Water that condensed farther from the Sun, in colder regions, tends to have more deuterium. By measuring this ratio in interstellar comets, scientists can infer how far from their parent star these objects formed. 3I Atlas probably originated in the outer reaches of its home system, beyond where its star's planets orbit, in a cold frontier similar to our Kuiper belt. The presence of organic molecules in 3I Atlas raises tantalizing questions about how life's building blocks spread through the galaxy. These organic compounds, carbon-based molecules like formaldehyde and hydrogen cyanide, are not life themselves, but they're the chemical precursors from which life could potentially arise. If interstellar comets carry these organics from star to star, they might be seeding planetary systems with the raw materials for biology. This process, called panspermia, has long been a speculative idea in astrobiology. Scientists estimate that a small fraction of interstellar objects might even impact planets rather than just passing through a system. Over billions of years, across countless star systems, some impacts must occur. Material from one stellar system gets physically delivered to planets in another system, carrying chemistry and perhaps even frozen microorganisms across the cosmic void. The probability for any single comet to impact a planet is extremely low. Space is vast, and planets are small targets. But given galactic timescales and the sheer number of wandering objects, these deliveries become inevitable. This mechanism could, in principle, transfer not just organic molecules, but potentially even living cells, if any exist frozen in cometary ice, and survive both the journey and impact. It's a slow process, incomprehensibly slow by human standards, spanning millions or billions of years between deliveries. But time is something the galaxy has in abundance. The Milky Way, is over 13 billion years old. That's enough time for countless exchanges, enough time for material ejected from one system to fertilize another, enough time for chemistry and perhaps even biology to spread. So the evidence building from 3I Atlas and the other interstellar visitors paints a new picture of the galaxy. Material flows continuously between stellar systems, carried by these wandering comets and asteroids. The timescales are enormous. Journeys might take millions or billions of years between stars, but time is something the universe provides in abundance. The Milky Way has existed for over 13 billion years, enough time for countless exchanges to occur through this slow galactic circulation. Star systems aren't isolated islands, but nodes in a vast network, connected by frozen messengers on journeys longer than human comprehension. Chemistry flows between them. Perhaps even the seeds of life flow between them. A pattern emerges clearly. Our sun's family shares deeper connections with the broader galaxy than we ever imagined possible. You're still here, still awake, still drifting with us through these stories. Take a slow breath. Notice how your body feels a little lighter now, as if gravity itself has loosened its grip just slightly. We're traveling through space together, you and I and everyone listening in the quiet dark, floating through facts like ancient comets drifting through the void. There's no rush, no destination, just the gentle momentum of curiosity carrying us forward. If you're still here with me, perhaps this is the moment you might share this piece with another searching soul. Just a thought, drifting past like starlight. Let's continue. The discovery of 3I Atlas comes at an interesting moment in our understanding of exoplanets. We now know that planets are common, perhaps even universal around stars. Thousands of exoplanets have been discovered orbiting other suns, with many more likely existing undetected. These planetary systems show remarkable diversity. Some have giant planets orbiting closer to their star than Mercury orbits our Sunday. Others have planets orbiting in extreme ellipses. Each system formed according to the same basic physics, but produced unique architectures. If planets are common, then the ejection of planetesimals during planet formation must also be common. Every planetary system, in creating its stable configuration of worlds, likely throws countless comets and asteroids into interstellar space. The galaxy's population of wanderers grows continuously. These ejected objects carry information about their home systems in their structure and composition, like tree rings recording seasons or ice cores preserving ancient atmospheres. Interstellar comets preserve conditions from their formation era. The minerals in their dust, the ices frozen in their nuclei, the organic molecules trapped in their structure, all formed under specific conditions of temperature, pressure, and chemistry. By analyzing what we find in objects like 3I Atlas, we learn about environments we'll never visit. We discover what kinds of molecules form around different types of stars. We map the diversity of planetary system chemistries. Each interstellar comet is a library containing volumes of information about its distant birthplace, written in a chemical language we're learning to read. The speed with which 3I Atlas moves through space tells us about the violence of its ejection. Remember, it's traveling at 58 kilometers per second relative to the Sun's rest frame, much faster than typical solar system objects. To reach that speed, something energetic had to fling it away from its home star, probably a close gravitational encounter with a giant planet, a world like Jupiter or Saturn, massive enough to significantly alter trajectories. In our solar system, Jupiter acts as a kind of gravitational slingshot, either capturing objects into modified orbits, or more commonly, accelerating them enough to escape the Sun entirely. 3I Atlas likely experienced something similar billions of years ago, a close pass by a massive planet that changed its fate forever. That violent encounter happened in another star system, around another sun, so long ago that the stars themselves have moved. The galaxy rotates. Stars orbit the galactic center at different speeds depending on their distance from it. Our sun takes about 200 million years to complete one orbit. In the billions of years since 3I Atlas was ejected, its parent star and our sun have followed completely different paths through the galaxy. The star that birthed this comet might now be on the opposite side of the Milky Way. The planets that ejected it, if they still exist, orbit a sun that 3I Atlas will never see again. The comet's journey has been not just through space, but through galactic time. Tracing that journey backward is nearly impossible. Astronomers can project 3I Atlas's trajectory back through time, calculating where it came from, based on its current position and velocity. The comet approached from the direction of Sagittarius, from the galactic thick disk. But that tells us only the general region, not the specific star. The thick disk contains millions of stars. Any one of them could be the comet's parent. Moreover, gravitational perturbations from passing stars, from giant molecular clouds, from the overall galactic potential, all would have slightly altered the comet's path during its long journey. After billions of years, these small effects accumulate, making it essentially impossible to pinpoint the exact stellar system from which 3I Atlas was born. Its specific origin remains forever mysterious. But the unknowability of its origin doesn't diminish the information 3I Atlas carries. We don't need to know which specific star it came from to learn from its chemistry. The molecules in its coma, the elemental ratios in its dust, these data points don't depend on knowing the parent star. They reveal conditions of planetary formation in a system different from ours, somewhere in the galaxy, sometime in the past. That's valuable on its own. Each interstellar object adds one more data point to our understanding of how planetary systems form and evolve across diverse environments. We're building a statistical picture of galactic planetary systems, learning from the samples that drift to us through the cosmic dark. The organic molecules detected in 3I Atlas are particularly significant for astrobiology. These compounds form through various processes in space, on dust grains in molecular clouds, in the atmospheres of dying stars, on the surfaces of icy bodies exposed to radiation, in the interiors of comets heated by radioactive decay. Once formed, organic molecules are remarkably stable in the cold of space. They can survive for billions of years, frozen in cometary ice, traveling between star systems, waiting. When a comet like 3I Atlas passes near a star and begins outgassing, these ancient organics are released, creating opportunities for them to land on planets. This is one possible mechanism for distributing life's building blocks throughout the galaxy, a slow but steady seeding process. Consider the implications if this process is common. Whenever a new star forms and gathers planets, it's not starting from scratch chemically. The molecular cloud from which it formed already contains organic compounds synthesized in previous generations of stars. As planets coalesce and comets form in the outer system, they incorporate these pre-existing organics. Then, as giant planets form and migrate, they eject many of these comets into interstellar space. Some of those wandering comets eventually pass through other, younger stellar systems, delivering organics formed elsewhere. It's a kind of chemical inheritance, where each generation of planetary systems receives complex molecules from earlier generations. Life's building blocks don't need to form locally. They can be imported, carried by interstellar couriers like 3I Atlas, connecting stellar generations across time and space. This perspective transforms how we think about life's origins. Traditional theories assumed that life began with simple molecules on Earth, which through chemistry and energy became more complex until life emerged. But if complex organic molecules arrive from space, already partially processed, already showing some molecular complexity, then the starting point for life's origin is more advanced. Planets don't begin with just simple molecules. They're seeded from birth with more complex chemistry, delivered by comets and asteroids, both from their local system and potentially from interstellar space. This doesn't solve the mystery of how life begins, but it changes the initial conditions. It suggests that the chemistry leading to life might be easier than we thought, given a head start. Halfway through our journey, the answer to our question begins to emerge. Could 3I Atlas change how we understand space? Yes, it already has. Space is not the empty void we once imagined. The darkness between stars hosts an invisible traffic of wandering objects, each carrying chemical information from its birthplace, each potentially delivering that information to other systems. Star systems are not isolated. They're connected by these travelers, slowly but continuously exchanging material over cosmic timescales. The galaxy is revealed as more dynamic, more interconnected, more alive with exchange than previous generations understood. And we're only beginning to discover this hidden network. 3 confirmed visitors in 8 years suggest many more remain undetected. The conversation between stars continues, written in wandering ice. And imagine, even when everything seems empty, space is always full of invisible travelers. The space inside and around you is never truly empty. Imagine you're floating on a calm lake, but beneath the surface, there's always gentle current, always movement. Right now, somewhere in the darkness between stars, comets are drifting, silent, patient, carrying messages from suns we'll never see. Let each breath guide you to realize time is yours, a separate stream that only you are living. While the vast universe continues its ancient dance, this second you're breathing, listening, is unique. Cherish the present moment, and we continue drifting. The closest 3I Atlas will come to Earth occurs in late December 2025. On December 19th, the comet will pass at a distance of about 1.8 astronomical units, roughly 168 million miles away. That's almost twice the distance from Earth to the Sunday. There's no danger, no possibility of impact. The comet will glide past harmlessly, already departing the solar system, heading back toward the interstellar depths from which it emerged. By that point, it will be visible only through larger telescopes, a dim smudge fading into the background stars, gradually becoming indistinguishable from the countless other faint objects that populate the night sky. For observers with 8-inch or larger telescopes, 3I Atlas remained visible through late 2025 and into early 2026. The comet moved through the constellations Virgo and Leo, gradually dimming as it receded from both the Sun and Earth. Its magnitude dropped below 12, requiring dark skies and patience to spot. Amateur astronomers shared their observations online, contributing to the scientific understanding of the comet's behavior. These amateur contributions matter. Professional telescopes have limited observing time, but dedicated amateurs can track objects night after night, documenting changes, noting details. The study of 3I Atlas became a collaborative effort between professionals with sophisticated instruments and amateurs with dedication. As 3I Atlas moves farther from the Sun, it gradually goes dormant. The warming that triggered outgassing diminishes. Jets of gas and dust slow, then stop. The bright coma fades as particles drift away or fall back to the nucleus. Eventually, the comet will return to its original state, a dark, frozen chunk of ice and rock, too cold for sublimation, too faint to detect. It will continue moving outward, crossing the orbit of Jupiter, then Saturn, then Uranus and Neptune, taking decades to reach the outer solar system before finally departing into interstellar space once again, invisible and silent. The exit velocity of 3I Atlas will be essentially the same as its entrance velocity. Gravity works symmetrically. As the comet fell toward the Sun, it accelerated. At perihelion, it moved fastest. Then, as it climbed back out of the Sun's gravitational well, it slowed, losing exactly the energy it gained falling in. When it finally crosses the boundary, where the Sun's influence becomes negligible, it will be moving at about 58 kilometers per second relative to our star, the same hyperbolic excess velocity it had entering. Conservation of energy is perfect. The Sun gives the comet a gravity assist, bending its trajectory, but ultimately returns it to interstellar space, unchanged. After leaving our solar system, 3I Atlas will wander for millions or billions of years before encountering another star. The distances between stars are vast. The nearest one to us, Proxima Centauri, lies over 4 light-years away. At 58 kilometers per second, fast by earthly standards but quite modest on cosmic scales, 3I Atlas would need about 5,000 years to travel just 1 light-year. To reach even our nearest stellar neighbor, over 4 light-years away, would require more than 20,000 years of continuous travel through the dark. And that's assuming it happens to be heading in that direction, which it almost certainly isn't. More likely, it will drift through the void for eons before randomly encountering another planetary system. During its long journey through interstellar space, 3I Atlas experiences conditions we can barely imagine. The temperature hovers just a few degrees above absolute zero. Cosmic rays, high-energy particles from distant supernovae, and other violent events constantly bombard its surface, slowly altering its chemistry. Occasionally, a speck of interstellar dust, traveling at different velocity, impacts the comet. These tiny collisions gradually erode the surface. Ultraviolet light from distant stars, though faint, slowly breaks chemical bonds in surface molecules. Over millions of years, these processes transform the comet's outer layers, creating a weathered crust, different in composition from the pristine interior beneath, a crust that protected ancient ice through cosmic time. This weathering is one reason interstellar comets might behave slightly differently from solar system comets. When 3I Atlas approached the Sun and began warming, the outer crust had been exposed to billions of years of cosmic radiation and interstellar dust impacts. This processed layer might sublimate at different temperatures or release different molecules than fresh ice would. The steep brightening curve observed in 3I Atlas could partly reflect this ancient weathering. The comet's surface isn't pristine material from its formation. It's material that remembers eons in the deep, altered by slow processes, carrying in its very structure a history we're only beginning to read. The trajectory of 3I Atlas might seem random, but it's determined by gravity. Everything that has mass exerts gravitational pull. The comet feels the Sun's gravity most strongly, of course. That's what bent its path as it passed through our system. But it also feels, however weakly, the gravity of the giant planets, especially Jupiter. These subtle tugs barely affect the comet's motion, but they're not zero. Over its journey through our solar system, Jupiter's gravity, though the planet was far away, slightly altered 3I Atlas's trajectory. When the comet leaves, its path will be ever so slightly different than it would have been had Jupiter not existed. In the larger galactic context, 3I Atlas responds to many gravitational influences. The Milky Way's overall mass distribution creates a gravitational potential that guides all motion within the galaxy. Stars orbit the galactic center in roughly elliptical paths. Objects between stars, like our comet, also orbit the galactic center, following their own trajectories. Occasionally, 3-eye Atlas might pass near another star, feeling a gravitational tug that changes its velocity or direction slightly. Giant molecular clouds, regions where new stars are forming, contain enough mass to gravitationally influence passing objects. Over billions of years, these countless small perturbations add up. The comet's trajectory becomes chaotic, its path through the galaxy essentially unpredictable beyond a certain timescale. This gravitational perspective reveals something profound. Nothing in the galaxy moves independently. Everything is connected through gravity's infinite reach. Every mass influences every other mass, however slightly. The Sun affects 3-eye Atlas. Jupiter affects 3-eye Atlas. Distant stars, though light years away, exert pulls too weak to measure but nonetheless real. The comet's motion is determined by the cumulative gravitational influence of everything in the galaxy. It's not traveling alone. It's dancing to a complex gravitational music composed by billions of stars, tracing a path through space that responds to the galaxy's entire mass distribution. Everything is connected. Scientists modeling the population of interstellar objects estimate that on average, 1 or 2 objects larger than a few hundred feet pass through the inner solar system each year. Most go undetected. They're too small, too faint, moving too fast, or simply in the wrong part of the sky when we're looking elsewhere. Improved detection systems like ATLAS and the upcoming Vera C. Rubin Observatory will increase discovery rates dramatically. Within a decade, we might be detecting several interstellar visitors per year. What now seems extraordinary, a visitor from another star system, may become almost routine, each one offering new insights into galactic planetary system diversity. The Vera C. Rubin Observatory, expected to begin operations soon, will revolutionize the search for interstellar objects. This facility will gently sweep across the entire southern sky every few nights, capturing everything that moves or changes, building a continuously updated portrait of our cosmic neighborhood. Its sensitivity and coverage are unprecedented. Computer algorithms will automatically compare new images to previous ones, flagging anything that has moved, brightened, dimmed, or appeared. Most of these changes will be known objects, asteroids, comets, variable stars, but some will be new discoveries. Among them, inevitably, will be more interstellar visitors. The discovery rate should increase dramatically. What took 8 years to find 3 objects might soon become monthly detections. With increased detection rates comes statistical power. Right now, we have only 3 confirmed interstellar objects, making it dangerous to draw broad conclusions. Are they all comet-like, or was Oumuamua something different? How do their compositions vary? What's the size distribution? These questions need dozens or hundreds of examples to answer reliably. As detection improves, we'll build a catalog of interstellar visitors, studying their properties statistically rather than as individual curiosities. We'll learn what's typical and what's rare. We'll understand whether our solar system's comets are representative of comets throughout the galaxy or somehow unusual. Pattern emerges from numbers. The study of interstellar objects connects to broader questions about planetary system architecture. Why do some stars have hot Jupiters, giant planets orbiting extremely close to their star? Why do others have planetary systems much more spread out than ours? The answer likely involves planetary migration, gravitational interactions, and the ejection of material. Systems that produce many interstellar objects are probably systems that experienced violent gravitational scattering, with planets migrating and ejecting smaller bodies. By studying the population of interstellar travelers, we're learning about the dynamical evolution of planetary systems, seeing the products of processes that shape the architectures of worlds around other stars. Each wandering comet tells a story of distant chaos. The galaxy reveals itself as more dynamic than we imagined, with matter constantly flowing between stellar systems, carried by these silent messengers on journeys measured in millions of years. This circulation happens so slowly that it's invisible on human timescales, yet over cosmic ages it becomes significant. Every star system contributes wanderers to the galactic population. Every system occasionally receives visitors from elsewhere. The flow is bidirectional, creating a vast, slow exchange that connects the galaxy's stellar neighborhoods. What seemed like absolute emptiness between stars is actually filled with this patient traffic, invisible unless we happen to catch one passing through. This realization changes our mental model of the galaxy. Instead of picturing stars as isolated lights in darkness, we should imagine them as nodes in a vast, loosely connected network. Material flows between these nodes, carried by wandering comets and asteroids, taking millions of years to make each transit, but inevitable given cosmic timescales. Information flows too, encoded in chemistry, written in the composition of every traveler. The galaxy becomes more dynamic, more interactive, less a collection of separate systems, and more a single interconnected entity, slowly mixing and exchanging across its spiral arms. Our solar system is one node in this network. We've sent material outward, comets and asteroids, ejected by Jupiter's gravity, perhaps now drifting through interstellar space, destined to pass through other stellar systems millions of years hence. We've also received visitors: Oumuamua, 2I Borisov, 3I Atlas, and likely many more that went undetected. This exchange places us in context. We're not isolated. We're participants in galactic-scale processes. The Kuiper belt beyond Neptune might contain not just objects born here, but also captured interstellar visitors, immigrants that arrived from elsewhere and were gravitationally caught, settling into orbits around our Sun, hiding in plain sight among native-born objects. Detecting captured interstellar objects in our solar system would be challenging, but not impossible. They should have unusual orbital inclinations or eccentricities, trajectories that don't match the general pattern of solar system bodies. Their compositions might be subtly different, showing elemental ratios that don't quite fit. Some astronomers have proposed searching the outer solar system systematically for objects with suspicious orbits, candidates that might be captured visitors. If found, these would be incredibly valuable. They're interstellar objects that aren't leaving, objects we could study in detail, perhaps even visit with spacecraft someday, touching material from another star without ever leaving our solar system. The concept of visiting an interstellar object captures the imagination. ESA's planned Comet Interceptor mission, scheduled to launch in 2029, is designed to do exactly that. Rather than launching toward a specific known target, Comet Interceptor will park at a gravitationally stable point in space, waiting. When a suitable target is discovered, either a pristine comet from the Oort cloud, or, if humanity is fortunate, an interstellar visitor, Comet Interceptor will intercept it, flying alongside and deploying probes to study it up close. It's a mission designed for opportunity, accepting uncertainty about what it will study in exchange for flexibility. The idea of intercepting an interstellar object represents a profound shift in how we explore space. Traditional missions launch toward known targets, specific planets, moons, asteroids. The destination is determined before launch. Comet Interceptor inverts this model. The mission launches first, waiting in space for a target to appear, ready to respond when opportunity arises. It's reconnaissance by patience rather than by planning. If an interstellar object passes through the inner solar system, while Comet Interceptor is waiting, humanity might achieve the extraordinary, touching something from beyond our solar system. studying material that formed around another star, bringing distant worlds within our reach. Even without visiting interstellar objects directly, we can learn from them remotely. Spectroscopy, analyzing the light that passes through or reflects from an object, reveals its composition. Different molecules absorb and emit light at characteristic wavelengths, creating a unique spectral signature. By examining these signatures in the light from 3I Atlas and future interstellar visitors, we decode their chemistry without needing to touch them. It's remote sensing at cosmic distances, reading information written in light, learning what elements and compounds exist in distant worlds by catching and analyzing the photons those worlds send our way. Light carries information across the void. The arrival of 3I Atlas coincides with humanity's growing awareness of exoplanets and the diversity of planetary systems. We've detected thousands of worlds orbiting other stars, seeing planets of every size and configuration. This context makes interstellar objects more meaningful. They're not abstract curiosities, but samples from those diverse systems we observe indirectly. Each interstellar comet is a direct sample returned from an exoplanetary system, delivered to our doorstep by the galaxy's own motion. Studying them connects telescopic observations of distant worlds with laboratory-style analysis of actual material. They bridge the gap between distant observation and direct examination. The future promises more interstellar encounters. Survey telescopes will discover additional visitors. Missions like Comet Interceptor might intercept one. Scientists will analyze their chemistry in increasing detail, building a database of compositions from across the galaxy. Over decades, patterns will emerge. We'll learn which molecules are universal and which vary. We'll understand how planetary system chemistry depends on stellar properties. We'll map the galaxy's chemical diversity through the visitors it sends. What began with Oumuamua's surprise arrival might become routine science, the study of galactic planetary systems through their cast-off material, a new field of astronomy born from watching wanderers pass through our home. Perhaps the most profound implication is philosophical rather than scientific. The arrival of interstellar objects challenges our sense of isolation. We've long thought of Earth and our solar system as separate, unique, alone. These visitors remind us we're part of something larger. The galaxy connects us to other worlds through these traveling ambassadors. We share atoms, molecules, perhaps even the building blocks of life with distant systems we'll never visit. The universe reaches out to us through every interstellar object that passes through. We're not alone, isolated in space. We're embedded in a vast, ancient network of connections. 3I Atlas has taught us that our solar system is not an island, but a port of call on cosmic ocean routes we're only beginning to map. Traffic passes through. Material arrives from elsewhere, bringing information, chemistry, possibilities. Material also departs, carrying our own system's signature outward to distant futures. This exchange connects us temporally and spatially to the broader galaxy. We're part of the galaxy's circulation, its slow mixing and sharing of matter across space and time. The realization transforms our cosmic address. We don't live in isolation. We live at an intersection where paths of ancient travelers cross our home. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Comets orbit. Planets orbit. Stars orbit the galactic center. All are circles, cycles, endless journeys through space. Like your breath, inhale, exhale, exhale, a small cycle within the vast universe. You are also part of that eternal movement. 3I Atlas was ejected. It traveled. It arrived. Now it departs. And the cycle continues. You don't need to hold on to anything. Let everything unfold in its perfect order, like these cosmic wanderers silently traveling their paths, unhurried, unresisting, simply existing. We're almost there now. Consider what it means to share molecules with worlds you'll never see. The carbon in 3I Atlas was forged in a star that exploded before our sun existed. Those atoms crossed light years, incorporated into a comet, traveled for eons, and arrived just as humanity developed technology to detect them. We're connected across space and time through chemistry. Every atom in your body has a similar story. We're all made from fragments of distant events, scattered across the galaxy. The galaxy operates on timescales that humble human perspective. 3I Atlas has been traveling for perhaps billions of years. Our entire civilization occupies just a few thousand years. To this ancient comet, human existence is a brief flicker. Yet here we are, observing it, learning from it, using tools we invented to understand a visitor older than our species, older than many lineages of life on Earth. But our recentness doesn't diminish our significance. We're the universe becoming aware of itself, matter organizing into patterns capable of comprehending cosmic processes. 3I Atlas is just ice and rock, following blind physical laws. It doesn't know it's traveling. We do. We observe, we analyze, we learn. In us, the universe gains consciousness, gains the ability to study its own history, written in wandering objects. The arrival of each interstellar visitor reminds us that the universe is larger than our immediate experience. We live on one planet, orbiting one star, in one galaxy among billions. Our sun is unremarkable. Yet from this ordinary world, we reach out through telescopes and mathematics, understanding things far beyond direct experience. We build knowledge from light, decode messages written in chemistry. 3I Atlas came from somewhere we'll never identify specifically, but we know it came from somewhere real. A planet ejected it through a process we understand. It formed in a protoplanetary disk, subject to the same physics that shaped our solar system. Everything in its composition formed through chemistry we recognize. The universe operates by consistent laws. What happens here happens elsewhere. That consistency makes the universe comprehensible. This universality of physical law is perhaps the most fundamental discovery of modern science. Gravity works the same everywhere. Chemistry is identical across the cosmos. The periodic table is universal. Stars form, planets coalesce, comets crystallize according to processes that don't change with location. This means we can learn. The tools we develop here apply universally. The cosmos is knowable. But knowable doesn't mean fully known. Each discovery reveals new mysteries. Oumuamua's acceleration remains unexplained satisfactorily. The exact origin of 3I Atlas is unrecoverable. Questions always outnumber answers. This is science's beauty. The more we learn, the more we realize we don't know. Every answer opens new questions. Every visitor from beyond brings new puzzles. The journey has no end point. In this context, 3I Atlas represents both an answer and a question. It confirms material crosses between star systems. It demonstrates we can study material from beyond without traveling there. But it also asks, how common are these exchanges? Do they affect planetary chemistry significantly? Could life spread between stars? What other surprises hide in the darkness, waiting to pass through? The study of interstellar objects is young. We've detected 3 confirmed visitors in 8 years. That's barely enough to establish that the phenomenon exists, let alone understand it thoroughly. Future decades will bring more discoveries, more data, better instruments. The patterns will clarify. What seems mysterious now might become routine understanding. This is the beginning of a new field. Imagine describing this moment to someone from a century ago. They knew of one solar system, ours. They suspected other stars might have planets, but had no evidence. Detecting a visitor from another star system would have seemed pure fantasy. Yet here we are. We've found thousands of exoplanets. We've detected interstellar visitors. We can analyze their chemistry. So could 3I Atlas change how we understand space? It already has. Space is not empty void separating isolated stars. Space hosts travelers, connecting stellar systems through slow but steady exchange. The galaxy is more unified than we thought, more interconnected, less a collection of separate parts, and more a single dynamic system. Boundaries between star systems are permeable. Material crosses them. This understanding ripples through related questions. If material exchanges between systems, could microorganisms frozen in cometary ice survive eons in space, then deliver living cells to new worlds? It seems improbable but not impossible. The question shifts from, can it happen, to how often, and does it matter? The galaxy might seed its own worlds. Even if life doesn't travel between stars, the building blocks might. Amino acids, nucleotide bases, organic compounds more complex than simple molecules. All these could accumulate in interstellar comets, delivered to new planets, shortening the chemical path from sterile rock to living world. The galaxy might quietly encourage life's emergence through patient deliveries across billions of years, making biology more likely, more rapid, more widespread. The philosophical implications extend beyond biology. 3I Atlas teaches that separation is less absolute than it seems. We feel isolated because we can't travel to other stars. But those worlds touch us through their cast-off material. The galaxy connects itself. We're not isolated observers looking at unreachable destinations. We're participants in galactic processes, receivers of messages written in ancient ice. So yes, 3I Atlas has changed how we understand space, and it continues teaching. Every new observation, every spectral line analyzed, every comparison with other interstellar objects adds understanding. The change isn't finished. As more visitors arrive, our comprehension deepens. The revolution that began with Oumuamua's surprise appearance continues. The galaxy's conversation with itself becomes clearer as we learn to listen. But perhaps the deepest change isn't scientific but emotional. 3I Atlas transforms space from hostile emptiness into a medium of connection. The darkness between stars becomes less frightening when we know it carries travelers. Those vast distances remain unbridgeable by human technology, yet matter crosses them. The universe is smaller, more intimate, more connected than perception suggests. This intimacy exists at cosmic scale. We're connected to distant stars not through journeys we can make, but through shared chemistry, shared physical processes, shared membership in galactic systems. The atoms in our bodies were forged in stellar furnaces, ejected in supernovae, drifted through space, incorporated into the cloud that formed our Sunday. We're literally made of stardust, and so is 3I Atlas. By recognizing our place in this cosmic network, we discover that every atom in our bodies participates in processes larger than ourselves. Processes that shape galaxies, birth stars, and connect worlds across space and time. We're not the center of anything. Our planet is ordinary. Our star is unremarkable. But we're not separate. We're part of them. We participate in galactic evolution. This embedding gives existence a different flavor. We're not aliens in an uncaring universe, but expressions of that universe's inherent creativity. The same physics that formed galaxies formed planets, formed life, formed consciousness. We're not outside looking in. We're inside, looking around. To study 3I Atlas is to study indirectly, the processes that made us possible. The comet will leave. It's already leaving. By the time you hear these words, 3I Atlas may have passed beyond Jupiter's orbit, growing colder, dimmer, returning to dormancy. Eventually, it will be too faint to observe, swallowed by distance. It will resume its billion-year journey, perhaps passing other solar systems in the distant future. But the message it delivered here remains. We've learned that space connects as much as it separates. We've learned that our solar system participates in galaxy-wide processes. We've learned that the universe operates through connection and exchange. When you look at stars now, you might think not just of distant lights, but of possible sources of wandering comets. And we've sent travelers toward them. Comets ejected from our solar system are now wandering through interstellar space. Millions or billions of years from now, one of our comets might pass through another planetary system, where beings we can't imagine might observe it, wondering where it came from, learning about our sun from chemistry frozen in its ice. In this exchange, the galaxy becomes more than a collection of separate objects. It becomes a kind of organism, slowly mixing and distributing matter, maintaining connection between its parts through these wandering messengers. The timescales are vast beyond comprehension, but the process is real. The galaxy connects itself through gravity, motion, chemistry, and time. 3I Atlas will be forgotten, eventually by most. Scientific papers will be written, data archived, and the comet will fade from public attention. But it contributed to a shift in understanding that won't fade. We now know, in a way previous generations didn't, that we're not alone, not isolated, not separate. We're embedded in a vast network. The real change 3I Atlas brings isn't in space. Space hasn't changed. The comets were always there, always traveling, always connecting star systems across cosmic time. The change is in us, in our understanding, in our perspective. We see space differently now, not as empty void but as filled medium, not as separator but as connector. The universe was always connected, and so our quiet journey through the cosmic pathways comes to a gentle close. We've traveled from the moment a telescope in Chile spotted a distant smudge of light, to understanding how billions of ancient comets drift silently between the stars, discovering along the way that the universe is far more connected than empty darkness suggests. From chemical signatures written in vaporizing ice to trajectories calculated across billions of years, we've glimpsed how the galaxy slowly mixes itself, sharing atoms and molecules across impossible distances. Interstellar visitors like 3I Atlas remind us that cosmic separation is less absolute than it appears. Much of the galaxy's connection happens in silence, in darkness, in patient journeys, taking billions of years. These wandering comets teach us about timescales beyond human comprehension. Without them, we might believe ourselves truly isolated. By pausing to notice one ancient traveler passing through, we glimpse the extraordinary hidden in cosmic darkness. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about unity of every atom, every comet, every star in the galaxy. You are not separate from this cosmic dance. You are a temporary pattern made of ancient star matter, the same matter that fills 3I Atlas, watching that comet pass through shared space. Think about the unity of all matter in the universe. Every atom in the comet, every atom in you, forged in stellar furnaces, scattered through space, finding temporary homes in new configurations. You too can dissolve into sleep like that. No boundaries left between you and rest, only the gentle flow of the universe continuing its ancient cycles. Let your entire being dissolve into the gentle darkness, into the soft pull of sleep. into the space between thoughts. Prepare for deep sleep, no boundaries left, only peace. If this gentle journey through cosmic connections brought you peace tonight, perhaps share it softly with someone else who's searching for stillness under the stars. It might be exactly what another restless mind needs to finally let go and drift. One quiet share, one peaceful night at a time. But there's no need to do anything now, nothing at all. You've traveled far tonight, farther than most journeys take you. Billions of years through time, light years through space, all while resting safely in your bed. You can allow these thoughts of wandering comets to fade now, like morning mist dissolving in sunlight, leaving only the peaceful calm behind. Let your breathing deepen. Let your body feel heavier, as if gravity itself is gently pulling you down into soft comfort, into the bed that holds you, into sleep. If sleep comes, let it carry you like Atlas itself, smoothly, inevitably, following trajectories set by ancient forces, moving toward rest as naturally as comets move through space. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, interstellar space will still be filled with ancient travelers. The galaxy will still be slowly mixing itself across light years and eons. Comets will still be drifting through the dark. But tonight belongs to stillness. Tonight belongs to you. Rest well, fellow traveler. And remember, you're not alone in this vast universe. You're connected to everything through the same atoms, the same physics, the same cosmic story. The universe that made you also made Atlas, your family in a way, both made of star stuff, both following your paths through space and time. Fall asleep to gentle facts. Where science meets sleep, dream deeper with bedtime science. Relax, listen, and drift into sleep. Good night.